Welcome back in the world of detailed engineering problems and contact mechanics. I will talk a little bit about a model that we have developed for checking how to deal with cyclic plastic deformation. So basically, we think in Leoben in our group that the cyclic plastic deformation that occurs in a rail has much things to do with crack initiation, but also the crack paths. So if we have a shear deformation field like that in the rail surface, those trajectories of the deformation, they more or less define also where the cracks will be. And on the other hand, when we reach a certain shear strain up here, that might also be an indicator or even a damage criteria. I think if we talk about ratcheting and failure to do ratcheting, that's something like that. So those are two cracks. There could be some head checks like that. There could also be some breakouts. Yeah. What can we do on the modeling side to capture that problem? That is some work that I showed 6 years ago in Chengdu. We took a full 3D model for the wheel rail test rig of the voestalpine, and we rolled over it. We saw where the contact patches would be, and then we thought about, good, we have now contact patches, they're non-Hertzian, there are maybe 2 of them, or could be more. What can we do with that? The thing is, we have some damage. How can we predict that? And then we went into 2D models, one with a crack, where we try to investigate what happens to the crack, what differences on that scale, or what parameters on that scale influence the crack driving force. And we also used a roughness model, where we saw that the small asperities and roughnesses influence the upper surface layers, some micrometers. The plastic deformation is highly influenced by this roughness. And basically, we thought about how to transfer loads from 3D to 2D. 2D is really good because you can use roughness, cracks very efficiently. Well, and one thing there was we just showed how it could be done, but we didn't really show how it was feasibly done. So now I introduce a quasi-static finite element model where we do something like that, but it's a little bit more basic. We use our standard. We have an elastic wheel because we're not too much interested in the wheel, but we have an elastic plastic rail at that point with a Chapoche type cyclic hardening model. The wheel loading goes like that. We have the wheel. Here in the middle there's a rigid part. We press the wheel on the rail. First with displacement, then with the force, with the normal force. Then we roll it with a certain creepage over the rail, and then it's moved back. And then we can cycle that for lots of cycles. Computational times for this model are in 3D 15 minutes and in 2D 10 minutes on some CPUs. What you don't see here is the 3D model. It could be really 3D, and at that point, we investigate loads where we have a conical wheel. While we're doing that, the voestalpine test rig can be set up to have a cylindrical wheel, which is rolling on the rail head. And then they can apply a slip, for example, 1.5% in an accelerating movement, and then they actually already measured plastic shear deformations for, I think, 700 cycles, 1,400 cycles, and many more cycles. So that would be our means of validating that. We're not showing stuff on that because we have to define all the details about the test, but that's where we're heading. Okay, and now I hope, before it didn't work that well, but this would be a video if it works. Could you try at least? Now it's working, great. Here you see, that's the 3D model. We press the wheel onto the rail, we roll over a certain distance, and here we see there was some plastic material behavior in there. We see some remaining von Mises stresses. Residual stresses due to that rolling. Great. Now the big question is, we can roll over a distance of something like that. We can roll over very long distance or a very short one. I think yesterday in the plenary lectures we saw that we need a certain distance of rolling for a certain contact patch to develop with slip and everything. And when we have plastic deformation, we need even a longer rolling length for something quite uniform of plastic deformation to develop. So that would be something I'll be studying in the next slides. And the other thing, of course, mesh size. What mesh size do we need to predict how much deformation we will have there? So the general model results that I'm going to show, I'm introducing them here. Here is our wheel, our rail. Then, of course, we have our contact patches. We have a contact pressure, the results of it, and then some traction or shear stresses on the surface. Okay, this would be one result. And the other one would be, we take this part of the rail, and then we look, after one cycle, how much accumulated equivalent plastic strain is there. In this case, it's 4%. And it's quite uniform over the distance, or the rolling length. The next thing is, how much displacement in the longitudinal direction is there. We have an accelerating wheel. That means that we have some shear displacement in that direction. And in this case, we have a maximum shear displacement of 0.23 millimeters after one cycle. And to compare different curves like that, or different results like that, we extract curves. And those curves mean that we look at each cross-section along the longitudinal direction and take the maximum value to see how uniform it is. We see here it's quite uniform. We also see it here in this diagram. The same for the displacement in longitudinal direction. This is not that uniform. Okay, now let's start looking at the contact patches. Here we have the results for a slip of 0%. We set up the 2D model to have the same contact patches in the elastic case with the Hertzsprung formulas. We see that fits pretty well. If we introduce elastic plastic material properties of the rail, we see that our contact patch is a little bit unsymmetrical for our first time when we roll over the plastic rail. If we introduce slip, we see we also have this shear or traction stresses here, and also the contact patch becomes a little bit asymmetric when we roll over it. What we also see here is the mesh dependency, and we see we get quite good and accurate contact patches if we already use 1 or 2 millimeters of mesh size. That's sufficient for that application. Now looking at those different mesh sizes and a certain rolling length, in this case it's 60 millimeters, we can look with a slip of 0% how uniform our plastic deformations. In that case, they're quite uniform. And our shear displacements. In that case, they're not uniform at all because we don't have any real slip and it's just an effect on the border. But we also see that the mesh size is not that much influencing that. For a slip, which is the more realistic and more relevant case, we see that our plastic deformations still increase with smaller element sizes. So we do not reach kind of a plateau or something there. But when we look at the displacements, which is really what interested us, it's already okay for 2 millimeter mesh size. So in that case, we say, the PEQ would further increase. We're interested in the shear displacements, so that's fine if we take a mesh size of 2 millimeters. And now we proceed. The next question is, how about the rolling length? Here you see many curves. The wider curves are the ones with a very long rolling length. And this is with 60 millimeters. 60, I think 120 and 200, something like that. We see it here, sure. And those curves that lie above each other, but have different line styles, those are 5 cycles of loading. So we see with more cycles of loading that in the 2D model, this is all 2D, we do not get very uniform plastic deformations over the length. So in 2D, whatever happens before and after it always influences it. The same with the shear displacements here. We see it depends on the rolling length, and the bigger the rolling length gaps, the bigger the shear displacements are. The good thing from that is that we see for the 3D model, it's already sufficient to take a smaller rolling length because we have material on the sides of the contact patch that kind of holds everything back in terms of plastic deformation. So we selected those rolling lengths for 3D and 2D and can now look at the results. Maybe this video is also working now on the big screen. Thank you. And we see the accumulated plastic equivalent strain in the 2D model and the 3D model. The legends here are different so that we see something, because, as we can see here on the right, the PEQ values are much bigger in the 2D case than the 3D case. Of course, it's a lot less resistance to shear displacement when you have a 2D model compared to a 3D model. And also the deformation depth is completely different. But the thing that interested us the most is the shear displacement that we can see here. If it's possible, please also run the video. Again, different limits, and we see how we get the shear displacement and how not uniform this is. We have some effects here, we have some effects here, and in the 3D case, it's a lot more uniform, and also the depth is a lot less. And when we look at the diagram over the 100 cycles that we used here, we see that that's more than an order of magnitude. Yeah. I didn't mention this in the beginning, but of course, in the rail, or in this test rig, we have a very long rolling length. But in the model, to keep it efficient, we should take a rolling length which is as small as possible, because double the rolling length is double the calculation times. Yes, that was what I wanted to say, basically. We have a fully automated 2D and 3D model for this cyclic rolling contact with plastic deformation. We see severe differences between 2D and 3D case in plastic deformation. And the next steps are to think about how can we speed it up and how can we take that as a basis for further going to contact patches validated with this. And the other one is to use a more sophisticated elastic plastic material model. And I'm very happy to announce that Knut Meyer, who presented on Monday, presented a quite good and interesting plasticity model for R260 rail steel. And I think this night he implemented this model into that model. So that's already one interaction that more or less was happening here, like with basic real modeling. Okay, thank you.